Hi, my name is Bob Cheesebro, and I'm a technical consulting engineer in Intel's compiler team. Welcome to the 7th in a series of videos covering Intel compiler vectorization essentials. In this video, we offer suggestions for how to determine how well your code is vectorizing. One method is by comparing a run of the code without vectorization to a run of code with vectorization turned on. Actually measure the speed up. If you have already inserted your OpenMP SIMD or OpenMP declare SIMD statements into your code and successfully compiled and linked, then this will be your vectorized version of the code. Be sure to keep a copy of this executable handy. Next, compile the code with the no-vec and also the no-SIMD directives. This effectively turns off all vectorization attempts. Copy this executable and name it as your non-vectorized version. Now run each executable. It is best to time specific vectorized loops against their non-vectorized counterparts. This can be done by inserting timers into the code just before and just after the loop in question, or by using a tool such as Intel VTune Performance Analyzer to determine the execution time for a given loop. Next, compare your vectorized speedup for that loop against what you expect theoretically based on the number of vector lanes you have. Note, if your code is time dominated by MKL calls, then you've probably already effectively been using vectorization and you're future ready. Assembly inspection can reveal the use of packed versus scalar or vex instructions. You can generate assembly to look at by using the -FA compiler switch. This is the most reliable method of determining exactly where vectorization was applied. You can scan the assembly, or grep it, for scalar, packed, or vex-encoded instructions. Another nice thing about this technique is that assembler listings contain source line numbers mapping generated code to loops in the source code. Another alternative is to consult the compiler opt report. In this case, the high-performance optimizer report can be obtained using the opt report with a numeric option switch. Here you would basically specify -opt-report with a numerical value such as 3, and also specify what phase of the optimization report you want to run. In this case, we would run the -opt-report-phase equals HPO for the high-performance optimizer. N represents a number that specifies the amount of detail provided. The default is 2. The max value is 3. Intel VTune Amplifier can also be used to determine vectorization. This example counts the packed SSE instructions for single, double precision floating point operations. Similar ones exist also for the 256-bit AVX instructions. Look at the SIMD _FP _256 packed either single or double keywords. Here are a few details about using the compiler vectorization report. The report has 8 different levels, providing different levels of detail concerning the vectorization process. You generate a report using the -vec-report option. You specify an integer value n to govern the verbosity. 0 is the default when you compile with something like O2. It tells the compiler to report no diagnostic information. It's useful for turning off reporting explicitly in case it was enabled on a command line earlier. Level 1 tells the vectorizer to report on vectorized loops. This is the default if you specified vec report but did not give it a number, n. 2 tells the vectorizer to report on the vectorized and non-vectorized loops. 3 gives a little more information. It tells the vectorizer to report on vectorized and non-vectorized loops and any proven or assumed data dependencies. 4 tells the vectorizer to report on non-vectorized loops. 5 tells the vectorizer to report non-vectorized loops and the reason why they were not vectorized. 6 tells the vectorizer to use greater detail when reporting on vectorized and non-vectorized loops and any proven or assumed data dependencies. It also provides information about data alignment. 7 requires the use of the simple Python script. It provides information such as expected speedup, memory access patterns, and the number of vector idioms for vectorized loops. For more information on the VEC7 report, please refer to this article. The article is called VEC Analysis, Python Script for Annotating Intel C++ and Fortran Compilers Vectorization Reports. The URL is given here. The whole subject of why a loop does not vectorize will be taken up in a more advanced set of training materials. In that presentation, we hope to discuss such things as flow, anti-output dependencies, lexically forward and backward dependencies, loop carry dependencies, and other topics such as alignment and temporal stores that can all help a developer successfully vectorize or better vectorize your code. In this case, the function fd is compiled with the vec_report3 switch. This report indicates that the loop was not vectorized due to a data dependence. That dependence is identified as a flow dependence. When we go back and look at the code, we see that the iteration n of the loop depends on iteration n-1 of the loop, and so this is a true dependence, and we would not expect to be able to vectorize this loop. A caveat: when using report switches concurrently with the inner procedural optimization switches, when using IPO, the optimization phase takes place at link time. For this reason, the developer would need to supply the vec_report_n switch to both the link command as well as the compiler command line. Here is a summary of what we have covered throughout this video series. First, we've explored the motivation for explicit vector programming, which stems from the multiplicative expansion of vector widths times core counts. We've looked at the SIMD-enabled functions as a means to provide a way to vectorize many user-defined functions. We've explored pragma SIMD-related clauses to provide explicit ways to vectorize loops. We've looked at the #pragma OMP SIMD clauses and their modifiers such as reduction, safe-len, and linear to allow vectorization of more candidate types of loops. And we've also looked at how the compiler reports help identify vectorization successes and failures. And that pretty well concludes this video series. Here are some references that you might want to take note of if you want to learn more about vectorizing your application. First is Art Beek's The Software Vectorization Handbook. Second is an excellent book by James Jefferson and James Reinders on the Intel Xeon Phi coprocessor high-performance programming. This has explicit chapters on vectorization and parallelization that are very key. Additionally, there are Intel software forums and knowledge bases and white papers at these locations. Also note that we have the OpenMP 4.0 specification at the openmp4.0.org location. Thank you for participating in our video series.